All right, so it says that you're live. You're live. Okay, then just make this. I think that if I click this presentation mode, it's gonna do.
It's fine. Just go to the.
No, no, it's doing this. Is there somehow like I can do something like this? What this is? Plaque,
I guess. Yeah.
tackle. So which one I should select? Yeah.
No,
No,
not
no.
yet.
Okay, I need to go away. And then this is the annoying thing. This was in last semester, the same thing.
I think it's something like that with your computer.
My computer?
Yeah.
You think in my computer?
Yeah. It
Okay.
doesn't happen for
Why? Okay, still something I need to do this duplicate.
it looks good.
Yeah, looks good. Okay.
At noon then?
Yeah, I'm thinking that we're gonna be here until noon
Okay, sure. I'll meet here.
because we have this career counseling to discuss today. This is a good place to be. Consider that there is this at least 5 seconds delay, so it's good now.
Yeah.
All right. Thank you, Suraj.
Yeah, it's like
What happened? So what happened to you guys? So you're not planning to come to lectures anymore.
the whole week is like full of events. Today was also a sliding event from KRK Build. So
Really?
yeah,
So what event?
yeah,
Sliding? Like you go downhill or?
yeah, 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 like going with a bus somewhere.
Ah, I see. I see.
From 12.
So
Till 10.
thanks, Suraj.
Also the bus back home. So
Okay, so this is a special week. All right, I see. I see. Anyway, so today we're going to discuss about it says here introduction to introduction of flexible multibody dynamics. But I still want to discuss about few matters related to three-dimensional multibody system dynamics. And basically, there are two things. I would like to close this thing about the four parameters. So we discuss about the Rodriguez equation that is not handy. It's not easy to use, and it's not often used. Actually, it's pretty much ever used. But there's something that is like uh, um, like another step forward from Rodriguez equation, and that's Euler parameters. And it's kind of funny that Euler parameters and Euler angles are completely different concepts. They have nothing to do with each other except the name is same. Euler angles is this based on three successive rotations. Euler parameters are four parameters. So they are different stories. And what is really often used in engines of computer when you do the computing is Euler parameters. Those are the ones that you can see a lot. So I want to explain about a little bit about the Euler parameters, and then the story that I mentioned that the big problem is that these rotational parameters, Euler angles, Euler parameters, they are not having direct relation to angular velocities. And that's the kind of like the main source of the difficulties in three-dimensional computing. That's where the most of the problems are coming from. But there is a kind of like a solution to get away from this problem, and it's called this famous G matrix. So it's like FBI. I think that they have this G-man, which is coming to solve whatever problem you might have. Here, the G matrix is doing the same thing. It's not solving all kind of problems, but the problems related to these description of angular velocities in three-dimensional space. This is something that I would like you to understand. And then we're gonna move on to, well, one more short story that we'll see how it's gonna go today is that we can discuss shortly about the robot kinematics. Because if you have participated in the class, like, well, I'm not sure about what are the titles of the courses, but the courses that are dealing with the robotics, most often they're dealing with something that is called 4 by 4 transformation matrix. Have you heard this before? Not. Okay. Anyway, so you have.
Yeah, but I'm an Erasmus student. I did maybe.
Okay, so it was in your home university. Okay, right. So anyway, so if you participate in Heikki Handru's classes, I think it is discussing about 4x4 transformation matrices and how you can do the kinematics of robotic systems more or less automatically when you have this 4x4 representation, more or less automatically. You still need to have a little bit of thinking, but once you have this kind of like a matrix that describes the topology of your robotic system, then the rest of the kinematics, it's just like that. It's a very, very simple thing. And it is having, of course, it's based on this kinematics we learn in a three-dimensional space. So that's the kind of like the last thing that I would like to shortly mention to you. And then flexible, but because so many other matters to discuss, maybe we are not even going to the flexible today. So it's going to be next week. Next week is a special week because I need to be off on Wednesday. I mean, not off, but I need to be out of my office. I need to go and make a visit in Lahti campus because there are members of the Finnish parliament that they want to hear some stories about this computational aspect, which is weird. And if I would be a member of the parliament, I would like to stay away from the computational aspects as much as I can. But these guys would like to learn about stuff that is related to computational things. So I need to be in Lahti campus on Wednesday. So there will be a substitute teacher. But good news is this, substitute teacher is the best we can offer to you. It's, guess what? Suraj. Suraj is really good. And Suraj, it was, don't remember why, but the last year too, when we had this class, exactly same topic. Again, I was forced to be out of my office, and Suraj was substituting me last year too, in the same subject matter. So he knows the business. All right, but then the big deal. I promised that we need to discuss, or we will discuss about the career counseling. Should we get started from the career counseling in the beginning? Or should we get started from the other matters and then go to career counseling? Which one you prefer?
First other matters than career counseling, because if career counseling is the end, we can maybe overdraw career counseling session.
Yes, you're right. So so what about others? So is it okay if we get started from career counseling? So you say get started from the career counseling.
Other way around.
Other way around. Okay. So first this one and then career counseling.
Yeah.
Because the career counseling is more fun stuff to discuss. Okay. But I want to do it this week because I heard that this deadline for some of the applications is already next week, Wednesday. Okay. So this is something that will be discussed as well. And I'm going to keep it in a way that the discussion is going to be 20 minutes. 20 minutes. But it's something that I would like to tell about myself, something that I also, a little bit instructions, how you should behave in interviews. This is something that I feel that is very, very important because I have seen many different kind of interviews. And what is the one that makes a positive impact? That's something that we can discuss. Okay. Right, so let's get started from not from flexible multibody dynamics, but three-dimensional multibody dynamics. And here's the story. So here's a summary of what we discussed a week ago. And I need to say this, when the last week, of course, was pretty chaotic because of the technical problems, but I'm so happy to be finally back here to deliver lectures. This is the moment of the week that I can focus on one only thing, because most of the time when I'm in my office is pretty chaotic. Million things simultaneously, organize million things simultaneously. Here, one thing only. That's beautiful. Okay, yeah, I just wanted to share that with you. All right, so three-dimensional kinematics. We already know what's the deal with that. So we know that we're going to use this body reference coordinate system that is attached to the body, and it's going to rotate and translate with the body. So there will be no surprises in that regard. The only difference between the planar and spatial is that the dimensions are different, of course. And that is not a big deal when you look at the vector R that describes where the body reference coordinate system is located at. And the vector R is a little bit of small font, but it's this guy here. This is having the three components because of the global X, Y, and Z coordinate axis. So of course it must have the three components. But then comes this complicated component, and that's a rotation matrix. And like we discussed, you have basically two choices, two alternatives. You can either use three parameters, and whatever you use in three parameters, you're going to face the problem of singularities. There's going to be singularity one way or another. Typical way of singularity is that you cannot differentiate what rotation is what, and it's called locking, which is not the mechanical locking, but inability to recognize differences between the rotations. That's what it is. And then comes the vector U bar, that is with respect to body coordinate system. So the one that is difficult is this guy, rotation matrix. All right, and how we can describe that? Yeah, so we can use successive rotations, and we can use other means and other methods that are based on three parameters, three rotations, and they are kind of natural for human to understand because body can rotate in three different ways, and three different parameters. That's understandable, clearly understandable. But whenever you're using three parameters, you have the problem of singularity. I mentioned this already millions of times, and this is implying that that's what I'm going to ask momentarily in my in-class quiz. All right, there is an exception here. This is something that I'm not a big expert in the field, but there's a very recent development in kinematics, and it's called something like Lie group kinematics. Lie group is a like own specialization in the mathematics, and if you're really interested about that, this is something that is a quite hot topic at the moment, because that is like a special way to treat the rotations. So it's a Lie kinematics, or actually it's a Lie mathematics, but it can be applied to rotation, description of rotations. So it's like this, it's spelled like math, Lie math. So if you are interested, you can take a look. So this is something that, but I need to give you a word of warning. This is going to be very, very painful. So it's not going to be easy to understand. Even the math is a bit different. But if you participate in the multi-body conferences, there is a good percentage of the presentations that are dealing with the Lie group, this and that. Lie group flexible bodies, Lie group kinematics. So it's like something that some people believe that it's going to make a major difference. Hard to say. It's really, really hard to say if it's really going to make a major impact. Anyways, three parameters are based on three successive rotations. And when you describe each of these rotations by 3x3 rotation matrix, the final rotation matrix looks like this. So it can be put in a writing like this. All right. This is what I took from Wikipedia. Gimbal lock is a loss of 1 degree of freedom in three-dimensional gimbal mechanism that occurs when axes of two of the three gimbals are driven in a parallel configuration. Locking is system into rotation in a degenerate two-dimensional space. So that's what it means. So it's like if you take a look at the gyro that is located in upper right corner of my slide, when the two axes are parallel, then you cannot tell what is what. You're losing your ability to differentiate the two rotations. And that happens quite often. And of course, you can monitor that by monitoring the rank of your rotation matrix. And then you see, okay, you are approaching this inability to describe what is what. I don't know if you watched the video about this aerospace application, the one that was in my slide last week. But there was an interesting story about how that can make a life difficult. I recommend you to watch that. It was the one that there was a lady in a front page. This is the very good YouTube video. All right. In three-dimensional, when using three rotational parameters, the problem is singularity, physical interpretation of parameters. That it means that it's so hard to understand what is what. They don't have a clear physical interpretation. Or then the final obstacle is that the usage of the three parameters is limited to small rotations only, meaning that you can only use it in plus minus 10 degrees or something like that. Is it going to happen today? Today it's going to happen, because I think we don't have these people, these hang-arounds in this class that are not really paying much of attention to teaching, and then they just give a shot. They give a shot whenever there's an in-class quiz. So in-class quiz is on, and we will get back to that momentarily. Look at this new thing. So I have this barcode. You can take a picture of that, and it takes automatically you to this Socrative. And now look at this, that the room is a bit different than it was. So it's LUT2, not LUT1. I mean, not LUT, but LUT2. Just take a picture of that, and it should take you to that class automatically. Can you try? So is what? Yeah. Let me just double check that by myself. Enter your name. Enter your name.
And it always says enter your name, but it's a number.
Oh yeah. This is when it says enter your name, it means enter your student ID number, because you can only get in if you enter your student ID number. Because remember we give extra points out of this. We need to know who is answering the correct way. And that's why you need to use your student ID number. So can you please double check that you're able to get in? Because
but it's normal, like, don't forget to say, like, you don't edit zeros in front of you.
Okay, yeah, important. So that's a good point. So if you have zeros in your student ID number, forget about them. So it's the first digit other than 0, that's where you should get started. So can you try if it works? So it works? So it works? Okay, so I'm not able to get in because I am not member of that class. I cannot enter the answers. Okay, but anyways, so can you do that? And then we get back to this after a couple of slides. All right, so this is something we discussed last week too. This is this Rodriguez equation. And again, the concept of the Rodriguez equation is that you have a vector, and then you're introducing like assisting vector that is unit in a length, and you attach the assisting vector to origin of your first vector, and then you introduce in the rotation that is amount of theta, and the amount of. Okay, so do we have a technical problem or what? He's calling me. He's a member of this class, so should I pick up the phone or not? Oh yeah, the thing is that. Okay, let me ask.
Somebody has access to the YouTube chat, maybe.
Yeah, that's the thing. So do we have a technical difficulties?
Slides are not changing. We cannot see anything rather than the past slide. And we are
Really?
in chat, but I think no one is watching.
Yeah, because no one is watching the chat. So still you see the first slide.
Yeah, we only watching the introductory slide. That is the 3B.
All right, so let me see what's the problem. I get call me if you don't see the other slide in let's say within a minute. Okay, thanks. So the problem is that slides are not changing. How come?
Maybe capture the wrong thing.
Because I'm capturing this one.
You can't see again that the thing is.
Should I capture window instead?
Maybe capture the whole screen.
Yeah, display like this. This will be safe choice, I think. Okay, so now I still need to do this. By the way, how is another teachers when they're streaming? They don't use a YouTube, so they use.
The other one, the mechanic dynamics, for it works fine. Like he just plugs it in and it's just.
This is Greg's course. Is it?
Greg's, machine dynamics.
You see?
I'm really bad at names.
You see.
Yeah.
So
You
he's
can ask him. He has like a similar laptop as you have, and
Okay.
he just plugs in.
Is he streaming via YouTube or something else?
I believe he's just recording.
Recording.
I think he's also streaming, but I'm not sure. Like he's probably streaming via Teams or Zoom,
Okay.
which probably makes also a lot of things easier.
Yeah, of course. But I don't want to use these Teams because
It should, in theory, actually be still similar because you're still just streaming.
right. Yeah, but I don't want to use it because there is a reason for that.
No. I mean, just
It shouldn't be. It shouldn't be. But it's always the YouTube is a bit more complicated. So it's always so many different things, so many moving components. So sometimes it is a little bit painful. So let me take a look at from YouTube channel. So how it look at the moment. Yeah, it's so hard to. It would be nice if I can use another computer to see if there's any comments from online participants. But this is a. So it's just so many moving components. Simulation laboratory course. Okay. Course. No, I don't. This one, okay. Live, it's live here. Yeah, and I see that is looking good. So it's looking good. So I can. Oh yeah, I just cannot keep it like this. Otherwise, there is a serious echo. Good. And I even see the comments, but the comments are very small font, so it's not easy for me to follow. All right. So let's get back to this to make sure that the online participants too can see it. So this was our first in-class quiz. So when using three rotational parameters, a problem is singularity, physical interpretation of parameters, usage of three parameters is limited to small rotations only. And the room today is LUT2, not LUT that I used earlier. All right. And by the way, I do not use a LUT class or the classroom because the creating of the simulation of mechatronic machine is still underway. And you might wonder when it's going to be ready. And the answer is this week. This week. There have been a little bit of work to create this simulation assignment, particularly because there is certain students we have we are pretty sure that they are committed to plagiarism. And the plagiarism is not a small thing here. So if there's a plagiarism, it's always a big problem. Like I said, it's okay to commit the crime, but make sure that you do the math, that the crime you do is benefiting your life, significantly. Plagiarism is not one of those things. The risk that if you get catched by doing the plagiarism the consequences are pretty severe, and what you can benefit is not so much. So the benefit and the risk is not in a balance. So it's not recommended to do that. Okay. Anyway, so the result will be available later this week. And now back to this. So Rodriguez equation, how I started to explain that we have this vector, and then we have this assisting vector. Assisting vector is attached to original vector, and then we're going to introduce amount of rotation, that is theta. We have 4 parameters because this is a vector that is in 3-dimensional space, so it consists of 3 components. And then we have angle theta. It's very complicated to use because human brains are not easy to understand this kind of the representatives. So it's extremely hard to use. And the one that is one step forward from that is Euler parameters, equally difficult to use. But how this is possible that we have 4 parameters describing 3 rotations? It's of course because this vector v is unit in a length. So we do have a constraint. So we have 4 parameters and 1 constraint. And the constraint is coming from the fact that the vector v is unit in a length. So when you compare the length of the vector v, that must be unit 1. And that's the constraint. And that's how it is. So 4 parameters, but they are having 3 degrees of freedom because 1 constraint. And that's how it works. And the constraint is this. So when I compute the length of my vector v, it must be 1. And that's what it is. That's my constraint. This, by the way, is a funny thing because when we made our first code, in-house code in multi-body system dynamics, so we wanted to, the very beginning we use Euler angles, and then after a little while we started to use Euler parameters. And Euler parameters, the one thing we forget to do was to use this constraint. And it was really weird simulation because even the simple pendulum was all of a sudden, it was a rigid body, it was getting bigger and smaller, and we were like, what is this? Did we invent the new kind of the dynamics? No, we did not. But we forget that there is this constraint. So the constraint needs to be added to list of constraints. Otherwise, it's not going to work. It's not going to be possible to do any kind of computing. Okay, so here's the one that is up in my slide. This is your rotation matrix. And you know that now is a function of vector v, and the vector v is expressed in skew symmetric form, and then the angle theta. That's my parameters. And then there's a fourth parameter. Now, in Rodriguez equation, rotation is described by 4 parameters, v1, v2, v3, and angle theta. These 4 parameters are coupled because angle is small. Angle is small. The vector v is unit in length. We are assuming a body to be rigid. Parameters are not coupled because a body can rotate in 4 different ways. One only is correct. Okay, this is not as easy. That I just said that what is a correct answer, but this is not as easy that what we started in the beginning. So what do you think about the first success rate? Is it going to be 100%? That's 100%. That's 100%. This one here is not going to be 100%, but it's going to be something quite high. I'm thinking like 85, 95, that neighborhood roughly. Still 90. Okay, so that's what you're thinking. So let's take a look. Okay, you guys ready? Did you enter your answer already? Oh yeah, you cannot yet because I first need to show you this one here. This one? All right.
No, if you go out of this presentation, stops completely.
Hold on. Why is that because I thought that my in-class quiz is on.
No, if you turn around, this presentation.
Hold on. Okay, here. Yeah, sorry. You don't see this. Okay. This is it. So we got 18 answers, which is, I think it is a good number. But what's the success rate? Is it going to be 100? 95. No, don't say that. But I think it is going to be 100. I think it is 100. So and we got more answers. And now this is never a good sign.
I'm not able to enter in the QR code. I see another answer.
Oh, yeah. Okay. So you don't see this one?
No.
Really?
The interpretation of matrix in case of vector work.
Okay. So did you use a room LUT2? Okay. So when you use this QR code, so it's giving you the wrong room. Okay. So can you just type socrative.com and try again?
Just type in and then type room.
Yeah, then you can type the room, which is LUT2, because so it seemed that accidentally I copied incorrect QR code from the previous room or something like that. Another course. There is even another course. Now I cannot close this activity, so I cannot copy that this time. But I got 18 answers, so I'm going to wait you guys. So type socrative.com, and then once you're there, then the first question is select room. You type LUT2. I cannot type here. I cannot write here. So it's LUT2. And then the next thing is give your name, and your name is your student ID number. Okay. Let me get back to this. So you ready? We all ready? So because I see that 18 answers, so I don't get any.
That was 90, then it was 18, then it was 90 again.
Okay, so we're ready. Okay, physical interpretation of parameters. That's not what I'm after here. Of course, it's always a bit hard to do the physical interpretation, but much easier in case of 3 parameters that is in a 4 parameters, because 4 parameters definitely are not give you any clear interpretation of what is that they are representing. Okay, so we're moving on. So the next one is in Röttequer's equation, rotation is described by 4 parameters. See slide. These 4 parameters are coupled because angle is small, vector v is unit in a length. We are assuming a body to be rigid. Parameters are not coupled because you know that the body can rotate in 4 different ways. If you select this one, then you need to explain me how it can be rotated in 4 different ways, 4 independent ways, because that would be a new physics. That would be a new physics, like completely new physics. So if you can figure that out,
Some type of quantum rotation.
that would be maybe something like quantum. But then you need to give a lecture about how is this 4th independent way that the rotation can take place. Yeah, it may be particle rotations. It could be the case. All right. I see that I'm a bit slow, so I will leave you guys here, and then I will jump back this one, and I'm gonna try the new thing. I will try this reading panel.
Yeah, I think that's fine.
This is good. Only problem is that I cannot write here. I cannot use my pen.
You can try.
No. But it's good enough. All right. Now, I was here. So what we're going to do next is that we're going to start calling these 4 parameters in a certain names. It's just a name game. And the name game going to give us another way of representing rotations. And the name game is called the Euler parameters. Very, very often used. So most of the cases when you look at the 3-dimensional software and the engine, how they do the computing in 3-dimensional space, they're using Euler parameters. Okay, how it goes? It goes such the way that you are first introducing the kinematic, the trigonomic relation as shown in this slide. I cannot use my pen, but with the relation that is saying that the sine theta is 2 multiplied by sine theta divided by 2 multiplied by cosine theta divided by 2. You're using that relation. And you substitute that to your Röttequer's equation. And then comes name game. Name game means that you started to call the components of this equation by certain names. This is going to be your Euler parameters. Again, remember the roots of Euler parameters are from Röttequer's equation. So it's coming from that. And it's still kind of like based on these 4 parameters that we use in our Röttequer's equation. But now we're going to call them differently. And how we're going to call them is going to be shown in this slide. So we say, okay, instead of saying cosine theta divided by 2, we say theta 0. And instead of saying v1, which is the first component of the vector v, multiplied by cosine divided by, sine theta divided by 2, we say theta 1. And that's how we're going to go. So each of the components will be having the different name. Now using these names, and when of course substituting the names to your 3x3 rotation matrix, you can get something that is located in the lower part of my slide. This is Euler parameters. This is what it is. Euler parameters. Euler parameters, still I have 4 parameters. So again, I must have this constraint. I cannot use them as it is. So I must introduce some kind of the constraint. And the constraint will be similar, or having the roots from the fact that the vector v is unit in the length. Here, it says that I can compute the length of my 4 parameters, these angles 0 to angle 3. And when I compute the length of my 4 parameters, that's supposed to be equal to 1. Again, 4 parameters, 1 constraint, meaning that there is a 3 independent way that the body can rotate, as is the case, because the body can rotate in 3 different ways only. Different ways. Again, remember there is independent ways that the body can rotate, and there's only 3 independent ways. Okay, so that's Euler parameters. And here's this constraint. This constraint can be expressed simply that when you compute the transpose of your Euler parameters multiplied by your Euler parameters, that's supposed to be equal to 1. This is coming, actually, when you look at this carefully, it is exactly the same constraint that is representing that vector v is unit in length. Okay, 4 parameters, very, very often used and painful for humans. Because if you give them, if you give any individuals the 4 parameters and say, can you please tell me how is a body orientation? It's hard, really, really hard. Computers, very good in this. Humans, not so much. That's why, and of course, there is a mapping between the 3 parameters and Euler parameters. And most of the software engines works in such the way that the pre-processing and post-processing, when the human is making the models, then actually, then this pre-processing is based on Euler angles. And just before you get started with the computing, you do the mapping. You're moving from Euler parameters because computation is so much more pleasant, so much more pleasant. Yep, that's what it is. I think there may be the only way to make an interpretation about the way that the human can understand these Euler parameters. Maybe you can use the help of ChatGPT or something, because ChatGPT is a computer-based thinking, so that might help you. By the way, I don't know if I mentioned this to you, but there's a team that we cooperate quite extensively, and the team is located in Innsbruck, Austria. And they've been quite busy of using ChatGPT and other large language models, because there are many other similar kind of ways than ChatGPT to build multi-body models. And it's quite surprising that these large language models can make models for you. So just define, okay, I want to use this software. Make a model of 4-bar mechanism, and here's a parameters of my first body, second body, and third body. Make a model to me. And just like that, model comes with no syntax errors, no any modeling errors. It's simple mechanism you can model like that. So that's quite surprising. And now, right now, they are also doing the same thing in a way that they're using handwriting. They're making simple mechanism using just a pen and paper. Take a picture of it and give that to large language models and say, make a model of this. And sometimes it can do it, but not all the time. Seems that these angles, it's still struggling with that. So it's not so strong in that. But if you make a better drawings, computer-based drawings, not hand drawings, maybe then it becomes a bit different. But it's quite interesting. Yesterday, we had our department meeting. Actually, it was a faculty meeting. It was entire faculty that was in that meeting. And that meeting was all about how to use AI. It was mainly large language models in teaching. And then later I got comments that maybe, maybe instead of asking from teachers how it can be used, we should ask from you guys. How is it you use large language models in your work, in your studies? Are you, by the way, using? Of course. Yeah, makes sense. Makes sense to use it. So do you know any tricks, any nice tricks, how to speed up the learning or?
I'm basically just going to get an answer from the lecture. So
Yeah.
I type in like the question and then try to interpret it in my own way.
Yeah.
And then try to write down what I understood.
Yeah.
From ChatGPT.
Yeah. So it makes sense. Makes sense. And this class we're going to learn some new hopefully we'll learn some new tricks, how to use these large language models and others. And the idea is that we're going to build these multi-body models based on large language models. And this is the one aspect. And then some of the models will be data-driven models. So they are not based on the equations, but huge amount of data. This is very much in a fashion as well. Okay, sorry about the sidestep. Okay, properties of rotation matrix. This is no surprises to us. So they are orthogonal. And if you build the vectors out of the columns of the rotation matrix, they're unit in length. Orthogonal is a beautiful feature because then the transpose is equal to the matrix inverse. It means that you're changing the mapping order from Conventional is from body reference coordinate system to global coordinate system, but if you have a need to do it the other way around, from global to body, you do the transpose. That will change the order you do the mapping. And you can test it that by doing this mathematical exercise as made in the very bottom of my slide. So that's how it works. All right. You cannot change the order of rotation. That's very important in a three-dimensional space. You can make an experiment by yourself. And you can say that, okay, Euler angles, my first rotation is going to be 90 degrees, and second rotation is at 90 degrees. And then you change the order, and you will recognize that your body will be having the different final configuration. So you cannot change the order of rotation. Planar case, that makes no difference, because we only have one axis where the rotation can take place. But in the three-dimensional space, you cannot change it. And that's something that is good to keep in mind. Robot kinematics. This is something that I promised to give a short introduction to that. And I don't think that I will explain about this Dynavit-Hartenberg. Most often used way to build the kinematics. So this is what I'm sure you'll learn about that, Dynavit-Hartenberg. But I'm going to explain what this is based on. And it's based on the kinematics we learned already, and how is it we can use this 4x4 matrix representation to build the kinematics as a big picture. That's what I would like to explain to you. And again, it's based on these same components that we have already learned. So there's going to be rotation matrix, and then there's going to be this vector U bar and R matrix. So we just relocate, we reorganize them, put them all in a 4x4 transformation matrix, and that's it. That's the way that we can build the kinematics. Beauty of this is that you can move from one coordinate system to another, and this is how you can build the kinematics automatically. So each of these matrix, each of the coordinate mapping is described by a 4x4 transformation matrix, and you keep on multiplying them, you can build more and more complicated kinematics automatically. All right, so it goes like this. Well, that the successive rotation, first of all, if we discuss about the rotations, you can take those into account by multiplying rotation matrices. This is part of the answer, the way we can build the kinematics. But what is missing here is a translation. So this only accounts what is a rotation of my final end effector, where there's a creeper or whatever that the robot is meant to be doing. So you know what is its orientation, but you don't know its location with respect to reference coordinate system. And this is something that we can take into account by modifying this representation, which is originally 3x3 representation, to be 4x4 representation. Additional component, of course, is going to be our translation. That's what it is. In the kinematics, robot kinematics, I wanted to say you this. It's a different story than most of the kinematics we do in a multi-body system dynamics, because what we know and what we want in a robot kinematics is that we wanted to have the end of the robot, the tool of the robot, to be in a certain place and configuration. The big question is how to reach this configuration by using this robot coordinate system, or the angles that are between the different bodies of the robotics. So the kinematics is quite a bit different than what it is in a multi-body system dynamics, because we need to understand what is a translation and what is a rotation. And of course, two different neighboring bodies in a robotic system, they don't have a 6 degrees of freedom, but they typically have 1 degree of freedom. Very often there's a rotational joint that is connecting the two neighboring bodies. Could be translational joint, it could be a combination of simple joints, but typically it's a 1 degree of freedom, and we need to know what this degrees of freedom is supposed to be to find the location where the end is located at. So this is inverse kinematics. That's what it is called. Making this difficult. Most of the robotic systems are redundant, meaning that you can reach this configuration in many different ways. Human hand is a good example about the redundant system. So I can have this configuration, this angle, this location, in many different ways, infinite ways actually. Human is not having any difficulties at all. I mean, it comes kind of naturally, but in robotic systems, not necessarily. And sometimes you have the task that you need to move your end effector according the line like this, and sometimes it goes fine, but sometimes it started to do like funny stuff like this. Human never do it. Of course, there is a ways like energy minimization and stuff like that that helps you, but this is what the robot kinematics is about. Inverse solution. And what we're going to do then is that we're going to take the equation that we know. There's only one equation we know, we have learned during the entire year. Nothing but the one equation. Is this kinematics, which is based on the body reference coordinate system. And again, we have a R vector that describes where the body reference coordinate system is located with respect to reference coordinate system, then the rotation matrix, and then the vector U bar. And that's the components. And what we're going to do is that we're combining these two components, translation and rotation, to one matrix representation. It's a substitution game. Nothing but the substitution game. Euler parameters was only name game. This is a substitution game. So it's not very complicated at all. You take your rotation matrix, you locate that in the upper left corner of your 4x4 rotation matrix. Then you take your translational component and you locate that in the upper right corner of your 4x4 transformation matrix. The one thing left is to make this to be square in shape, you have to add one row. And the row is going to be fully occupied by zeros, except the diagonal component need to be 1. This diagonal component is for some reason called like scaling number. And I don't know any reasons to scale the bodies to be anything else except not scaling it, meaning that the number needs to be 1. But if you put this number to be 2, then whatever you do the translation, they are scaled. Similar way that I say that, in the beginning when we made this multi-body in-house code based on Euler angles, the bodies were getting smaller and bigger because of this constraint was missing. Here, if this number is other than the 0, other than the 1, it's going to do the similar kind of unnatural scaling. All right, so that's what it is. Now, this is a part of the solution. The next kind of like a missing component is that now what we can do is that now we have a relation between this coordinate system and this coordinate system. And then if we have more coordinates, meaning more bodies in our robotic system, we can keep on adding these 4x4 representations. And then we can get more and more robot bodies into account. And when we do this, the kinematics comes automatically. You're just multiplying these 4x4 matrices together. That's all you need to do. That's all you need to do. This famous Denavit-Hartenberg method is simply taking use of the fact that, right now the way that I'm representing this 4x4 matrix is such that I have all these 6 degrees of freedom open. And what the Denavit-Hartenberg is doing is that is just opening some of the parameters, but not all. And that's what it's based on. So it's very, very simple method, and each of these coordinate systems are linked with the certain parameters only. And these parameters are called Denavit-Hartenberg parameters. My supervisor, when I was in Chicago, mentioned that he knew this Hartenberg. So he was actually in Northwestern University in Evanston, which is not, that is city next to Chicago. And Evanston and Chicago are like more or less the same city, I would say. But in Evanston, they have this super famous university, Northwestern. And Hartenberg was in that university. I don't know if this is true or not, but my supervisor mentioned that Hartenberg was working when he was 80-something years old. Quite amazing. I don't know if still developing his method or what kept him busy, but that's how I knew. That's what I know. I didn't know that, but I've been told that he was very heavy working man. Okay, that's 4x4 matrix. And it works like this. This is a simple numerical example. So I have, So again, I'm using here Euler angles, not Euler parameters, but Euler angles. And I have here the rotations that are taking place along the global z-axis. And then that's the only rotation. And then there's a translation. So what I do is that I'm comparing my 3x3 rotation matrix, and I have to do that in the upper left corner of my 3x3 rotation matrix. And then I do that translation. I have to do that in another missing component, another missing part of my 4x4 matrix. That's all I need to do. And then I take this U-bar vector into account that was given in my assignment. When you do the math, it gives you exactly the same solution that using the conventional kinematics. But again, the beauty is that now you can simultaneously account the translation and rotation. Not handy as it is here, but it becomes to be handy when you have more coordinates, when you have more bodies. That's what the coordinates are representing, because each of the robotic bodies having the one reference coordinate system. That's what this is based on. And now if you wanted to know where the D, which is hypothetically our end effector, where the tool is located at, what is its orientation and location? You can get it by building these transformation matrices between each of the coordinate system, exactly like I did in this example. And then you just not give the numerical value from them, but some of the values are parameters. Like, let's say if there's a revolute joint between this body and this body, then there's a revolute joint parameters that is left open. And then multiplying these matrices, you can know where this D coordinate system is located and how is its orientation. That's what the 4x4 matrix representation is about. Okay. If you want, I have a few slides. I think that I even have a little bit of stories, put it in a writing about this Dynavit-Hartenberg. But the Dynavit-Hartenberg simply comes from the fact that these coordinate systems typically in the robotics, they cannot move up as they want, but they can have 1 or 2 degrees of freedom. And that's how that is based on. Now, how you build this kinematics then eventually is that you're building matrix or table representation of these parameters. And once you have these parameters, then you do the substitution and everything will be ready after that. I'm going to show you a simple example next week, but very, very simple because that's not the main focus of our course. Okay. Happy? Good. One more thing. And then we're going to move on to flexible multibody dynamics. And this is this problem that I mentioned in the 3-dimensional space. And again, the problem is the fact that angular velocity is not the same than rotational parameters. I mean, time derivative of the rotational parameters. This is really, really confusing because, in a planar case, they are exactly the same. So if you have angle theta, that is representing the rotation of the body. If you differentiate the angle theta with respect to time, you will get theta dot. Theta dot is exactly the same than angular velocity. No difference whatsoever. 3-dimensional space is not. It's not. And regardless how you do it, I mean that if you can find it out that the way to represent the rotations in a way that they are equal, then you just come to my office. Of course, you're going to take over my office, of course, and then we walk together to rector's office. Rector is going to give you a professorship, just like that. Doctor's hat, of course, and then you continue, and I will go to do something else. So that's how it goes. So think about it. The next time you're walking home to your apartment, think about it, how you can do the rotations in a way that it's going to be exactly the same than angular velocities. So it's not easy. Many people have tried. Maybe the most promising now is this Lie group. So maybe the Lie group will eventually do it. Okay. It's related to everything then, of course, because then when we're using these rotational parameters, the rotational parameters will be our unknowns. So everything will be expressed by using these rotational parameters. We have to build some kind of bridge between the physical representation of angular velocities and accelerations and the parameters. And this bridge is something that is coming very, very handy whenever you're modeling the things. Because when you do the modeling, of course, components like inertia tensor, which we're going to briefly take a look, is going to be easy to give it to use in the parameters that the human can understand, like body reference coordinate system. So if you give it a inertia tensor using body reference coordinate system, your life will be pleasant. Comparing that, you're going to give your inertia tensor using 4 Euler parameters. It's going to be very, very hard to do it, almost impossible. But because the computing is based on 4 parameters, you need to build the bridge such that whatever is the way that you wanted to express your parameters, it can be mapped to the ones that are unknowns in a computational, in a computing. Okay, confusing. But let me explain this to you. So let me see what are the comments. Okay, all right. Right, so we get started from this, and then I would like to take a short break after that. Okay, so velocity of particles. So you know how is the kinematics of the way we wanted to express the particles in 3-dimensional space. Now, when you differentiate your position with respect to time, you will get velocity. Of course, you're going to get the velocity. And now, here comes something that is a bit confusing. This is where we kind of introducing this subject matter. This guy, of course, vector u bar dot, when we're dealing with the rigid bodies, that's going to be canceled out because the u bar is a constant vector, so it's going to disappear. But this one, this is a dot in 3-dimensional space, can be expressed in such the way that is a rotation matrix multiplied by angular velocity in a skew symmetric form. So it's a vector of 3 components expressed in a skew symmetric form. So when you're using this notation, this is how your velocity can be expressed. Of course, this one here is a vector u bar, and if you don't like the skew symmetric form, you can express it as a cross product, which is not typically the case in any of these derivations. They always wanted to use the skew symmetric form because it is implementation-wise, when you do the implementation, way more pleasant because it's just a matrix multiplied by whatever needs to be multiplied, vector or matrix. Now, this angular velocity here that you can see in this slide is not the same than time derivative of these rotational parameters, regardless how you do the selection. There's absolutely no way that you can make it same. But you can build relation, and this relation is built by using the vector G. The vector G is simply doing the mapping in a way that finally you can express your velocity by using generalized coordinates. I need to get back to this. Because here, the way the velocity is expressed, the parameters of the rotational parameters are hidden here. So they are not explicitly mentioned. So you cannot use this in your computer. So you need to make it explicitly expressed. That's what I wanted to do. And I can make it happen by using this famous vector G that is doing the mapping for me. I always need it. The shape, a form, or the matrix G ranges from, depending what kind of rotational parameters you wanted to use. It ranges. That's what it is. And in Euler angles, it looked like this. So this is a mapping. And in Euler angles, something surprising here is that if you look at the columns, the first column is representing z coordinate axis, as is the first rotation. Now if you're selecting this P, what is this? What is this again? P to be equal to 0, then this second one is going to be your x-axis. Z, x, Z. And now if you're selecting your theta to be 0, this is going to be Z coordinate axis. So it's kind of representing how the rotation took place in a very original representation of your Euler angles. Now this is the one that doing the mapping. And now it sounds like, okay, is this needed and what's the big deal about this? It's a big deal because now it's make it possible to use any parameters you want and any inertia representation you want because you have this relation that builds these two things together. And this is particularly handy when you have this inertia tensor. Inertia tensor is a representation of how is that the body resists the three-dimensional rotations. That's what it is representing to you. And now you can express that using any parameters you want. Okay, very, very complicated subject matter. And most of the cases this year too may be the question that is related to this particular subject matter is watered out in a midterm exam. Like how the inertia tensor can be related to acceleration of rotational generalized coordinates. 2 times rotational, so it's a typing mistake. Sorry about that. Okay, that's what we're gonna have a short break, and I'm gonna move on to flexible multibody dynamics right after that. I said that we're gonna close at noon, so we have like 15, 20 minutes before we need to move on to carrier counseling. How that sounds? Okay, 5 minutes. Is it off? Okay, 5 minutes. I see my camera is frozen. No, it's not. It's just that there's a pretty serious delay. Okay, 5 minutes break. Yeah, hold on, before you go. Let's see this. Okay, 22 answers, so it's much more than in the first case. So 22 answers, so are we gonna get 100%? No. But how high we can go today? 75, 85, 87, okay, 87. So if it's gonna be 87, 73, okay. Angle theta is small, but that's not the case. We never make an assumption about the small rotations in this class. So it's always a large rotations, always. Then assuming that the body is rigid, yeah, we do this assumption, but that's not what couple thinks. Because remember, these 4 parameters are coupled because, and then the parameters are not coupled, and then somebody's voting that too, because the body can rotate in 4 different ways. Absolutely incorrect.
People have actually voted, so we have a few presentation waiting for you.
Yeah. All right. So 2 more in-class quizzes today. So the next one, I'm going to show it to you already. So the matrix G is important. The one we just described, the one we just discussed, because it couples the local and global coordinates. No. Couples the angular velocity vector and time derivative of generalized coordinates. That's what it is. Describe the inertia properties of the body. No, not that directly. Couples the global and generalized coordinates. Global and generalized coordinates. That makes no sense. This is making no sense really. Global and generalized coordinates. There is this mapping that is coupling that, but this is this partial differentiation matrix. So completely different story. Nothing to do with the vector G, matrix G. So you know what's the correct answer. Yeah. Let's just say it. Yeah. That's the correct one. That is the correct one. But the online participants are not able to hear you guys. And they are, I want to give them, that you need to get the reward some kind that you come here physically. This is something that I don't know how to, what to think about this hybrid teaching because, I don't know if you remember when you met in the first day when you came to university. I said that you get the 2 big packages from the university. The one is a certain kind of thinking. We training this thinking when we look at this super complicated G matrix stuff and something like that to make sure that you're not getting confused. You still can have your clear mind and your clear thoughts even when we discuss about something that is extremely theoretical. This is one big package you learn from the university. But another equally important package is your networks. And now with this hybrid teaching, I'm not sure how well it serves in that particular way, Because if you're sitting in your apartment and watching these recordings or streamings, of course, you learn this complicated reasoning, but you don't get this networking. And the network is important. You need to get to know others. Simple like that. So maybe that's why the others are not here. They are in downhill skiing in Lapland or whatever place they went. So that's networking too. So you need to do that, networking. Okay, but now 5 minutes. 5 minutes and then we will be back. So it's 11:20, 11:25, 25, and let me do the math. Yeah, 15 minutes and then we are closing this stuff and then we're gonna look at the career counseling.
So you could maybe look on Windows. There should be like some kind of app or something where you have an overlay and you can draw on anything. It doesn't save onto the slides, but maybe during like the presentation you can have like this mode on, so you don't have like this troublesome thing, but you can still draw on the screen. I've seen it somewhere, but I'm not sure.
So how you do that? So you have a separate device like Apple.
No, like this. There should be in Windows some kind of option where you can just draw on the screen.
Yeah, maybe you're right about that because you know when I was putting this in a presentation mode, it was asking something.
In the bottom right, there's this pen.
Bottom right. Here.
Yeah. Do you see this pen with the swirly thing? No, not on the presentation, on the taskbar.
Somewhere here.
On the taskbar.
This one.
The taskbar is below. It's where the weather and the time is.
Here.
Yeah, the pen. Windows Ink Workspace.
Huh.
Okay, now
Okay, so what should I select here? Full?
can you whiteboard? No, not the dot, maybe? Okay, other options.
Pen settings. No. That's not the way to go.
It needs to be some kind of app. We can have a snippet of the whole screen where you can then draw on. You have whiteboard, but the whiteboard is also just empty space.
Okay, is it this one?
Yes, since this is drawing, but it doesn't update with the thing you're constantly displaying.
So can I write it here too? No, I can. I can. You can see this. So if I do this,
Probably then not anymore because you're not editing the slides anymore.
yeah, not
What
anymore.
are the other modes of the slides you can have?
Okay, so I should select, what should I select then?
What are the options again? You have like reads, the presentation.
This one?
The third one?
Third one, this one,
Normal?
this one.
The one with the 4 dots.
4 dots. This one, so I should select the pen
No,
again.
like the other presentation mode or whatever it is. Between read and the normal one.
Normal one.
But if you press draw with touch,
Where can I see this?
He now has like in the top on the section one. Draw
Okay,
with touch.
so can you, let me take a camera off. So video, okay, the camera is off. Can you show me?
Sure. I need to try myself. I'm not sure there's any option.
It would be, because it would make really life much more pleasant if we know how to do this. Because it's a bit annoying to go back and forth.
What is this option, for instance? It's a slide sorter, ink replay, slideshow, slideshow timings. But this is slideshow, right? This is not the wrong one. Present. I could maybe look up at home. Like for now, we can do this. But there should
Yeah,
be
okay,
something.
that would be nice. Because I want to use this one, but I hate this stuff that I need to connect and disconnect this computer. Is it, what do you think, what about this, is if I somehow use, no, this is, I shouldn't touch this. This is too high risk.
You see like the electromechanic.
So Jussi knows how to do it.
Yeah, he seems to have like an age he can control this stuff when it works. The other option would be maybe trying to simply hide this and this. I don't know how to hide the slides.
Ah, yeah,
But you can click on this, you can at least hide the upper selection.
like here.
No, here on the small arrow up. And this.
Yeah, so it could make this better already.
but if you try
I will ask from Jussi. So what should I do here? So I should put it in this mode? Yeah, right. Yeah. And I was somewhere roughly this area. Okay, so if we figure out this G, and the G is important. This, by the way, so this is the next question. So why this G is important? Because it couples the local and global coordinates, couples the angular velocity vector and time derivative of generalized coordinates. It would be more specific to say generalized rotational coordinates, but that doesn't make much of a difference. Describes inertial properties of body and not directly.
We discussed this right before.
Yeah, so that's how it goes. Now the kinematics will be now different. So everything will be in future based on G and generalized coordinates. This is what makes it possible to express the equation of motion. And when you do this, I'm going to just shortly explain how it is, because really what I would like you to be aware of is this G mapping. When you have this G mapping, you can use it in your your accelerations, and your accelerations, they will look like this. And now that is looking really, really bad, really, really bad. But this is something that if you remember how we did in a planar case, we expressed the generalized coordinates, acceleration of generalized coordinates to be more specific separately, and generalized velocity separately. This is something that's going to give you mass metrics, and this is something that's going to give you quadratic velocity vector. This is how the codes are made in multi-body system dynamics. And they are always based on this G, always G. And now this gives you the freedom to select these angular coordinates however you want. And the beauty of this is that when you're following this, this was exactly the same that we did in a planar case. So when you're following this, your mass matrix is going to look like this. This is your mass matrix. And something that is going to be forming here is going to be your inertial tensor. I want to highlight this because it's quite important, because now the inertial tensor here is expressed using global coordinates, body reference coordinate system, which is really pleasant, because then you know what is your mass moment of inertia with respect to three axes of your body reference coordinate system. You know how is your mass moment of inertia, your mass product of inertia. You can get it actually directly from any CAD software you want. And you can express that in using body reference coordinate system. And then the real computing, you can move any representation you want with help of G, because G is doing the mapping. So eventually, the mass matrix itself could be consisting of 7 times 7 components. If you directly get started with the 7 times 7, you will be lost. I can guarantee you that. It's going to be so difficult to express inertia properties using these Euler parameters that no one can do it correctly. But now because of the mapping, now it becomes to be possible. I don't know about you guys, but I discussed with my colleague from Wisconsin-Madison in one of the good universities in the US, and my colleague is teaching in a master level like I'm doing here too. And he says that he's forcing his students, each one of them, to build the multi-body software, multi-body code using three-dimensional space. So something like this. I feel that this is very, very difficult for master level students, but in Madison, Wisconsin-Madison, they seems to do it. So I don't know, what do you guys think? I think that I got 0 students in my class if I say, here we're going to create the entire code in three-dimensional space using these G matrices and stuff. It's going to be too hard, I believe. A little bit too hard. Okay, so that's the story about the three-dimensional space. Inertia tensor, of course, this is how the mass matrix look like. You have this mass, which is this identity matrix. So mass in a three-dimensional, three different directions. Then the one that is connecting the translation and rotation. And what is left in this lower right corner is your inertia tensor multiplied by G matrix. That's how it works. The inertia tensor consists of mass moment of inertia and mass product of inertia. Mass moment of inertia is always having the positive values. Problem in a mass product of inertia, it can be minus or plus, depending how you set your coordinate system. So it's a little bit hard to deal with. But again, please use your CAD software to do the computing. And the equation of motion eventually look like no difference. Okay, flexible bodies. Let me get started from this. And like I say, I wanted to explain your method that is extremely important in engineering, and that method is a finite element method. Finite element method that you may be already familiar with. I don't care, because I want you to understand the true nature of finite element method. Very often, finite element method is misunderstood, because the way to easily understand the finite element method is using the spring analogy. Explaining that there are two points that are connected together via springs. And finite element method is not at all about that. And sometimes you hear these stories that, you have these 2 points. Like I'm speaking about the beam elements. Like the beam elements that is representing this structure here. You have the node here, and you have the node here, and something that is between is empty space. Finite element method is all about the space between the nodes. It's all about the space. So it's getting started by making assumption, how is the space? How is this area between the nodes? Everything is based on that. So really the finite element method is, how is we describing something that is between these points, nodes? They're calling nodes. And that's what I would like you to understand, because, when you're using a commercial software, you're definitely not going to understand this concept. And if you're learning the finite element method using the spring stories, same stuff. It's not about the springs, but it's all about how you're describing space between the points. And it's described by using polynomials. You're aware of this already or not yet? Not yet. Okay. But it can be described by using other means as well, not necessarily polynomials. And something that is very much in a fashion is to use a little bit different representation. There is this isogeometric analysis that is no longer based on polynomials, but NURBS. NURBS, because NURBS are non-uniform rational B-splines. And these NURBS are the ones that are used in CAD software. So when you're making drawings in a CAD software, you are using actually NURBS. I'm sure you are not really, it's not really telling you that, hey, you're using NURBS. But yes, you are using NURBS to make it, whatever shapes you want. And now polynomials and NURBS are relatives, but they are not from this exactly same family. And the big problem in the finite element modeling is the conversion from NURBS to polynomials, and it is called meshing. Meshing means that you're representing your NURB structure by elements, which are based on polynomials. And those of you that have been using finite element method, you know that the most time-consuming step is a meshing. You need to do mesh, you're not happy with the mesh, you redo it, do it again, because there's something that you're not happy with. This back and forth phase, particularly if you're dealing with more complicated structures, it's really time-consuming. And now this isogeometric is using directly NURBS. So it's no longer based on polynomials, but non-uniform rational B-splines. What are those stuff? How it works? I'm not going to tell you the details, but I will give you highlights about how it works and how it's pretty handy in very complex geometries. So that's about it. But first thing, flexible bodies. This area is very, very exciting. And it's a little bit difficult too, because It takes you from rigid multibody dynamics to something that is more used in a structural strength analysis, finite Selman method. And it's somehow like the method that are somehow in a family of finite Selman methods. And it is conceptually very different than what we've been used to deal with. Because remember, so far, one body, rigid body, is described by using simple coordinate system, the body reference coordinate system, and parameters attached to that. And now when we're discussing about flexible bodies, then we need to do the discretization within the body. We have not discussed this earlier, but now we need to do so. So we need to start describing how many degrees of freedom we're going to use to describe flexible bodies. In theory, each of the flexible bodies, they have infinite number of degrees of freedom because infinite number of particles. Remember what we started. Every single body, infinite number of particles. And I say that, we can simplify the life by using the body reference coordinate system where the particle is not moving with respect to it. But now they can move. They actually can move because when I have the deformation, it means that yes, the particles are moving with respect to body reference coordinate system. We need to make a few very important decisions, like how accurately we're describing this motion, this deformation motion. And this is typically related to how many coordinates we used. And this is something that we're going to spend quite some time to make sure that you understand this concept. But first, I would like you to understand the finite Selman method itself, and then we're going to use it in multi-body system dynamics. That's my target. Reason to model flexible bodies is to increase the accuracy of the models. There is no other reason. That sometimes there is a reason that you want to get some quantities like strains and stresses. You cannot get them if you have a rigid body because rigid bodies, there is no deformation. No deformation, no displacement, no strains, no stresses. Zero stresses all the time. And now maybe there's a need that you need to know that the stresses or stress histories, strain histories, mostly stress histories. So then you must model your bodies as a flexible bodies. Remember, one of these early examples that I showed to you was this biomechanical case, where we modeled the human bones as a flexible bodies. Flexibility of bones is not really affecting the human performance. It's not like when I'm running, my bones are bending like seriously that you can see the deformation in my bones. No, you don't see that because the bones are rigid. They don't deform that much. But we modeled them as a flexible bodies because we wanted to learn the strains and strain rates during the exercises. So that was the reason. Okay. Now, these flexible bodies, this is something that making a decision when the body needs to be modeled as a flexible body, and when it's okay to model as a rigid body. This is a very difficult question, and there is no solution for that. In literature, they've been sometimes an attempt to give like some kind of rule of thumb when the body is supposed to be modeled as a flexible body. But seriously, it depends on your engineering knowledge, engineering common sense, engineering sense. Yeah, engineering sense, that's a correct word. So it sometimes improves quite a bit about the accuracy. Sometimes it's needed because of the strain history thing. But generally speaking, there is no rule, no way that know when the body should be modeled as a flexible body and when it is okay to model as a rigid body. So you can develop the method of your own. You can look at the structure like this and say, yes, flexible. You need to model as a flexible body. And then you can ask consulting fee as thousands of euros because of that decision. But again, no real way to find it out when it makes sense to model as a flexible bodies. Okay, then I have one more in-class quiz. When a body deformation needs to be accounted in a multi-body applications. And the options are when large force is applied to system, when natural frequency of the body is low. By the way, we're going to discuss about the natural frequencies too, which takes you close to the vibration analysis. And then the slender structure, where the thin structure is consideration. There is no general rule to make this decision. So which one is correct? And after this, we're going to move on to career counseling. So let me check myself here. G is important because couples, 96, really, really good, really good. Not 100, of course, but it's a 96. 86. Yeah, but that's good too. That's good too. That is good too. Okay, then the last one is when you can make this decision. And like I say, then we gotta get started from the finite element because we need to do this discretization. And how you do the discretization, how you describing the life between these 2 points called nodes. They could be more than 2 points because depending on the type of the element you're dealing with, yeah, it can be something completely different. So that's what we're gonna discuss a week from now. Okay, and then I'm gonna rush myself. I'm gonna take a look at that momentarily. And I'm gonna, yeah, I know that there's a lengthy story, so I'm gonna, here. Career counseling. Not that.
It worked actually.
Really?
Just click on presentation.
Yeah, but the online participants see it in an incorrect way, so that's the problem. So either you see it well.
Try it. Like, if it really works for us, maybe it works for them too.
So it looks good to you, but I think it is going to be not, yeah, not good. Online participants see it like this, so they don't see it as well. Maybe there's something that I can select here.
The problem is that Steve wants, for some reason, the presentation mode.
Can I select something like something here? Oh, no. Absolutely not that. Okay, so it's going to be like this. Okay, so let's get started. Career counseling. It's because of application period for summer positions is about to close. And it's extremely important to be active in this regard. And the one opportunity, of course, is that instead of finding the summer position, you can always consider to get started in your thesis work. And this is something that you can make quite a bit of use of from your summertime. Or you can even combine. That's possible too. So you can get the summer position, and then as a part of the summer position, you can get started in your thesis work. That's possible. But really what I wanted to say here is that career is not about what is going to happen this spring. It's more about long-term perspectives that I would like you to understand. And at least the time scale that I would like to keep it in your mind continuously is 5 to 10 years ahead from now. That's roughly what you need to take a look at. Not immediate thing. Of course, it includes the immediate things, but the bigger target should be a bit far away from what you're doing at the moment and what you're planning to do upcoming summer or next year or so on and so forth. But 5 to 10 years, something like that. And then something that I feel that is people often forget is that they seems to be overly demanding to themselves, really overly demanding. So you need to learn the way that you can give a credit to yourself. So whatever you accomplish something, like you passed the course, this is already a major accomplishment. Or when you're doing a good report, you need to make sure that you can give a credit to yourself because you are a student of highly ranked university. This is already a major accomplishment. The only best of the best can find a way to, let's say this class, seriously. It's not, you may think that, yeah, it was easy. Okay, maybe it was easy for you. But if you put yourself in a bigger picture, it's not easy. Most of the students, people in your age, are not here. Because there is a high selection, there is a high criteria to find a way here. So this is something that is good to be proud of and try to give a credit to yourself. I understand that it's important to give a high demands how to perform, but even more important is this credit. And maybe there's a way that you like to do a lot. Have an extra cup of coffee or go to a movie or something. Make sure you do that frequently. Okay, all right. Then something that I really want to emphasize here. You guys are already very good in theoretical aspects. No doubt about that. That's absolutely clear. But what is something that is there is always room for improvements, always. And I try to do this by myself, is this interaction with other people's communication skills, storytelling skills. You're never in a position that you're, okay, now I have learned everything. By the way, this kind of mindset, when you think that, okay, now I have learned everything, I have figured out everything a while ago, that's a big problem because then your way will be way down. So when you're thinking that there is still room for improvements, there is still, something that I need to get to know better, then you're always climbing up and you make yourself stronger. And as soon as you have this thing that I'm the best, I just figure out everything, then you know that I'm in my way down. So that's important to keep in mind. So cultural skills, particularly if you're looking for a position in Finnish industry, these cultural things are something that is good to be aware of. And this culture, Finnish culture is not that much different than any other European cultures. Definitely very different than American culture. Definitely very different than many of the Asian cultures. But European-wise, I don't see that big of a difference. But I see some differences. Like this is Spain, Spanish culture and Finnish culture, they're not the same. For sure they are not the same, but there are very different ways that the people behaves, but they are not that far off. Particularly when I compare Finnish culture to Japanese culture, Korean culture. They are very much different. They really are different. These cultural things are something that is, you need to be some certain level, you need to be aware of these things. And of course, there is always a debate like, okay, which really matters? Is it the broad knowledge or some really detailed, deep knowledge about one single subject matter? And I'm just saying that you need to make sure that you have a broad knowledge. You need to have a good common sense about number of engineering matters, because that's what typically the companies are really appreciating. If you say that, okay, I'm the best in, not in a finite element method, but certain kind of finite element analysis, they may say, yeah, that's great, but we don't use this kind of analysis, so go someplace else. So it limits your markets when you put yourself in a very deep specialization. So the specialization, you need to have certain area, but still the broad knowledge is something that is extremely important. And like I say, 10 to 5 years ahead, that will be something that is extremely important. And this interaction, communication, storytelling skills, you can practice that every day when you're here in a university, in your campus. Tell stories in a cafeteria to your fellow students. And think what are the stories they like, what are the stories they don't like. Or with your family members. Tell the stories and see what they like and so on and so forth. But the typical problem is that when the engineer people are telling the stories, it's not too enjoyable. And why? Because they would like to go directly to details. And this is the big problem. And I see that a lot. I see that even in application when people are preparing the research project or when they are applying funding to their research project. Most often they tell an awful lot about the partial differentiation, about delta power, this and that, but they forget to mention something that is very, very important. Like what is the problem that they're solving? Sometimes even something obvious like that, it could be missing. Too much about details, too little about what exactly you wanted to do. And the Scott Semken, that is our mentor in writing proposals, he's saying, always making jokes that, okay, you guys have so many tools to solve the problems, but you just don't know what is the problem. And it's often the case like that. So it would be a good idea to focus on the problem, try to explain that, and learning your communication skills like that. Okay. Now, you need to set the target. What is that you want? 5 to 10 years ahead. And then you need to work hard, but not overly hard, because sometimes I see these attempts that people are working like a month, as much as they can. They don't go home. They are spending all the time in the university, which, by the way, is no longer possible because I heard that nighttime you need to leave. But some of the students are already asking waivers that they can spend here night times. Yeah, of course, it's important to work hard, but there's a limit how much you can work because you need to make sure that you keep things in balance. This was 15 years ago. I got the doctoral student that wanted to finalize his doctoral dissertation in a record time. So he made an attempt. So he said that I'm not going to leave from my office. I mean, I'm going to stay in the university until my dissertation is ready. Not a good idea. Not a good idea. He was maybe several weeks in his office, but then he started to develop all kind of like medical disorders, including mental ones. So it's not really the way to go. And that actually slowed down his process quite a bit. So it's still good to find a way that you keep your life in balance, life in a way that is enjoyable. I understand that there may be a day or two, week or two that you need to really push yourself hard, but it cannot be every day like that. It just cannot, not possible. Something that I see a lot, that people get confused about the details. And now I'm not saying about the mathematical details, but the career counseling details. Good example is that people are taking the grade of the one single course too seriously. I see that, this class, simulation of mechatronic machine, some people are scoring 4 out of 5, and they're extremely disappointed, extremely. They are like, I need to kill myself. I cannot continue my life because 4 out of 5. They're like, come on, you're not reading this well. So it's a 4 out of 5. This means very good. Difference, 5 out of 5, 4 out of 5 is insignificant. No one cares. We don't care. So when we're making selection the people, when we're selecting people as a summer trainers, we don't care. We simply don't care. What we care that the person is able to express thoughts in a clear manner. That's what matters. So make sure you're not getting too much energy to something that you don't benefit much. This is something that is really important. Time management. This is extremely important. So make sure that there is a time for do something fun. Make sure that you're monitoring how you're spending your days. I'm recommending my thesis workers to get this diary and explain in a diary what you've been doing this day. And it's quite surprising because you might have a clear plan. This is how I wanted to spend my time. But when you're monitoring that, it's not actually at all according to your plans. So the plan and monitoring both are important. Monitoring may be even more important than the planning itself. You need to somehow force yourself to focus on that way. And I got to show my time schedule to you momentarily. And then the way that I'm monitoring that too, but the way it goes. And don't put too much in your plate simultaneously. It's not needed. It's not needed to be a Superman. It's okay to do something that is reasonable. This is my time management. And what I have in my computer is like I have a separate software that I'm clicking when I do things. Okay, I'm spending time with my, this is a little bit of small font, but it's a doctoral student research. When I'm communicating with this is me, not you, but this is my planning. Doctoral student research, master level teaching. It's quite a bit. Maybe the sector is smaller at the moment than it was a little while ago. Project planning, administration, community service, external funding. These are the stuff that I do. I want to limit myself to that. But then there's like mix of things that happens. This mix of things should be having the small sector in your time management only. How to make it happen? I'm saying that the monitoring is the way to handle it. So we'll look at that, and once you see it, then you understand. Yeah, I use too much time to chatting around with the people. That too is a lot of fun, and it's important, but not the only thing you need to do. I did not. I was checking this watch all the time. I did not realize that we only have 6 minutes left. Okay. Here's extremely important thing to understand. I think I mentioned this to you in the last presentation too, but you need to, like I say, look 5 to 10 years ahead. Your first extremely important decision is about to come. Are you going to go to industry or academia? I wanted you to understand that this is a big decision because transition from industry to academia, academia to industry is getting to be increasingly difficult. It was easier a little while ago, but not so simple anymore. Let me explain you why. Because, first of all, if you're selecting your thesis work to industry, okay, then the industrial companies, they fall in love with you and they really like you a lot. And then they offer your position in the industry. Okay, you take a position in the industry, whereas your fellow students, they take a position in academia. Your fellow students are going to go their direction to doctoral studies. And when they go in their doctoral studies, they started to produce papers. And when there's an opening in academia, the first thing they ask, before they say hello, they ask, do you have a doctorate degree? And if you say, no, but I'm planning to get one, they will say, okay, bye. We are not going to continue this discussion anymore. So you must have a doctorate degree. There's another question, again, before they say hello. How is your publication? Human value in academia is based on publications. You go to industry. You're not going to produce any papers at all because most of the stuff you do, it is confidential, semi-confidential, and even if not, it is confidential. You simply don't have a time to put things in a forum that is accepted as a journal paper. It's not going to be possible. So you are not going to get papers. And it used to be the case that academia was really appreciating your experience in industry. That was at the time that I was young. Yeah, 100 years ago. It was like a nice policy that you need to get certain level of knowledge from hands-on understanding, like how the company is performing and so on and so forth. Even I do. I do. This is confidential information, but I'm a hardcore academics. But I do have a history in companies. I do. So when I got my doctorate degree, I spent some time in a paper making company. If I would be in your position and if I do the same, I would lose the opportunity to continue in academia because academia and industry, they are separated so severely, jumping back and forth hard, which is shame. I felt that it's a shame, but that's what it is. Now when there is a position opening in academia, they almost never, I think never, they don't say that the practical understanding is needed. They don't say that anymore. It used to be the policy a little while ago. There was a requirement. You must understand your subject matter in a way that you can cooperate with the industry. Not needed anymore. My understanding that in Germany, they still appreciate this more than they appreciate in many other places. It's hard to be a professor if you have no relation to real, industrial work. Is that a case? Pretty much so. Yeah, that's my understanding too. But in US, if you look at the professors in US, no, they are not coming from industry. They're coming directly from academia. And you know that each of the universities worldwide are copy-pasting what happens in US, university-wise. Tenure system was not a practice in Finland a little while ago. It was a practice in US already long, long time, and now we have it. And it's the same as in Germany too. Tenure track system. Yeah. It wasn't the practice here. It was a different thing. And now it's a tenure track. Everything is tenure track based. Okay. So that's what I wanted to say. The thickness of the arrows are telling that the majority of the people are going to industry. And they stay there. There's a certain people that goes to academia and then they can move to industry. That's possible. But this arrow that's moved from industry to academia is thin. Possible, but keep in mind that it's thin chance only. Not so simple. Define your strength. Try not to look at your weaknesses. And this is that the font size is telling you how it goes. So the strength is something that you recognize, okay, this is where I'm very good. Focus on that stuff. Each of us, we have the weaknesses. Now this is well, every single human has a weakness. That's what it is. And you just need to somehow find a way to live with that. Find a way to live with that, and simple like that. My great weakness is my dyslexia. Big problem. Big problem. Not simple, so it makes life, if I would somehow would get the medication to get rid of that, I would take it immediately. But it's something that is gonna be with me always be with me, and it's never gonna it's never gonna fade away. Never. I just need to find a way to deal with that. And it's sometimes not nice, but what are you gonna do? What are you gonna do? Nothing you can do. So I need to tell a story that when I was in this industrial company, I made a very comprehensive report about certain kind of bearing system. And this was, of course, at the time it was put it in a writing in Finnish. And this went to a very wide audience, this report. Because of this dyslexia, goddamn dyslexia, I misspelled the bearing name consistently incorrectly. So entire report was every single time that I mentioned this bearing name was incorrect. Embarrassing, very embarrassing. But what are you gonna do? It happens. So that's what I mean about every single one has their weaknesses. It is what it is. You just need to find a way to live with that. But the strengths, focus on that. And define what is your strengths. Okay, try not to be perfect. This is important too. But there are cases like your thesis work. You need to put an effort to try to be as perfect you can. And whatever you put it in your plan, put 20% overheads because you need it. You definitely need it. And then get mentors, peers, good people, career counselors, networking. And you need other kind of networking than your colleagues, your students. You need to get to know professors. You need to be in not you need to be a good buddy of me, but you need to be in a connection to me that whenever you're looking for a position, you can send me an email and say, hey, I'm looking for this position. Can you give me something went to my throat. So can you give me a letter? And I can. I can do that. I can help you. And I say that we're getting close to the end of the lecture. So what the heck went to my throat? Okay. Mentors, peers, good people, career counselors. Good people. That's what you need. Try to get in good connection with the good people. Because they doesn't necessarily change your entire life, but they can help you in details.
You will not do it with good people.
No, you need to get to know Suraj as well because, whenever you're applying a nice position in academia or in industry, you can ask, okay, Suraj, can you be somebody that is recommending me? Can you give me a letter? Yes, we do that all the time. But you need to, participate in the classes. Sometimes I get the request from the students that I've never been in my class. I don't do that. That's not possible. There is a limit how much we can do. Okay, now, this is the final slide. Make sure that this is this year open positions. Very highly recommend you to take a look at this website, which is tech.fi. There's instructions how to do career planning, how to apply positions, how to do the documentation, how to find positions, because they have a list of open positions in this website. Extremely important website. This particular time of the year, you need to take a look at this continuously, because I think it is the list of positions available is changing all the time. Toolkits, everything is available there. They're also telling you what to ask as a salary, but go easy with that. Go very easy with that, because they are saying, this is a union-based, and unions, they always want to emphasize that the salaries are this high. And I think that they cannot give you a recommendation that your summer worker salary should be unreasonably high. And that can kill your possibilities to get the position. So go easy with the recommendations and ask from your fellow students what makes sense to ask. Because sometimes they can ask, okay, we can hire you, but you need to tell your salary. And then you say, yeah, my salary is 15,000 euros per month. And they're going to say, okay, goodbye. So that was it. So you need to be reasonable. What is reasonable? That depends. These guys, they're shooting very high. I think they're going to say something like 5,000. I checked. No, not necessarily summer job, but they say like engineers generally got like 5,000. Starting salary, starting salary. I don't know what they say about the starting salary.
I just checked.
4,000. That's a starting salary.
I just checked, like, they have published, like, in bold letters on their website, academic engineers' median salary goes to 5,500 euros.
Which is true. Which is true. But that's the entire community.
Yeah.
You guys are not necessarily considered as experienced. So, okay, that's my last slide. Okay, and it's already 5 minutes past interviews. We're gonna just be honest, demonstrate interest. This is something that is important. Listen to questions, stay focused, because sometimes it happens so often that there's a question and the answer is not related to question. So it's okay, this individual obviously have a problem to understand or hear. And do not be late. This is a big deal. It happens every now and then. You come late because it's not a big deal. Finland, you come late, you can consider yourself out from this particular position. They are not going to hire you. And that means a minute late, you're out. I don't know if it is a minute late, but you're 10 minutes late, typically they don't want to see you anymore. They don't. Okay, you don't need to tell everything. You can be selective. That's okay. There are, because it's by the law, there are many things that they cannot ask, and you don't need to release that. There's many things that are private information. You can keep it as a private information. Not a big deal. Okay, now let's go back home, and the next week, Suresh will be here. Okay, so let me close the recording.
That actually depends on the tests.
So, okay, let me take a